Welcome to another lesson of the course Curves in Engineering and Architecture. We are in the second part of the course, namely Curves in Road Safety. In Module 6, we would like to learn more about transition curves and other relevant issues in geometric design of roads. Lesson 6.3 is about how to draw tangents to curves and more. Remember that in Module 4, we focused on horizontal alignments that result in comfortable and safe roads. We found the clothoid or Cornu spiral as a good transition curve because its curvature, that is, the size of variation of tangent direction, is proportional to the arc length traveled. After that, in Module 5, using mathematical tools as derivation, integration, and polynomial approximation, we got parametric equations of a clothoid. These equations give us the position of each point on the curve in terms of arc length traveled along this curve. Using these parametric equations, in Lesson 6.1, we gave a procedure to lay out a clothoid in the field. In Lesson 6.2, we dealt with vertical alignments and we got the parabola as the best possible shape, asking that the rate of change of grade or slope was constant and using again the notions of derivation and integration. Now in Lesson 6.3 we deal with combination of horizontal and vertical alignments as roads are three-dimensional objects, and we suggest some further problems and reading related to curves in road safety. As a road is a three-dimensional object, horizontal and vertical curves should coincide to provide a good aesthetic impression. Sometimes safety consideration suggests that horizontal curves be extended beyond vertical curves in order to avoid hiding the beginning of the horizontal curve from drivers approaching it, for example when horizontal curves coincide with sharp crest vertical curve. In addition, either in horizontal or vertical curves, in order to get a flowing line, it is better to use long curves and short tangents than long tangents and short curves. This is especially true when the deflection angle of horizontal tangents or the difference between grades is small. But how to draw the tangent line to a curve at a point? First, draw any secant line S passing through P. Second, draw a semicircumference omega of center P, limited by secant line S. Third, draw a family of secants through P, let's say A, B, C, D, giving the corresponding points on the curve and the corresponding points on the semicircumference. Fourth, from the points on the semicircumference, carry the elements PA, PB, PC, PD, and PE over the corresponding secant, same orientation. Fifth, the resulting points A'1, B'1, C'1, D'1, and E'1 define the error curve epsilon. 6. Call P1 the point of intersection of the semicircumference omega and the error curve epsilon. Then the tangent to the original curve at the point P is the line joining P and P1. Finally, we introduce the concept of superelevation or banking of curves, whose goal is to counteract the centripetal acceleration of a vehicle that is rounding a curve. Maximum rates of superelevation are established first to prevent slow-moving vehicles from sliding to the inside of the curve, and second, in urban areas to keep parking lanes relatively level and to keep a reasonable difference in slope between the roadway and any street that intersect it. Again, in road safety, the clothoid curve provides for a good superelevation transition because its curvature varies linearly with the arc length traveled along the curve. Thanks to the property, side friction increases linearly through a clothoid superelevation transition when it is traversed constant speed. You can learn more about curves in road safety by looking at the complementary material of Module 6.